Hello, my name is Braden Marconi, and today I'll be presenting Physics 2212, Lab 3 on circuits. The purpose of this lab was to understand how resistors, capacitors, and batteries interact with an electrical current circuits. Using circuit analysis, we predicted several electrical quantities and then compared those predictions to real experimental measurements. From the results, we observed two main outcomes. First, the change in electric potential around a complete circuit loop is equal to zero, which confirms Kirchhoff's voltage law. Second, in an RC circuit, increasing the resistance increases the charging and discharging time of a capacitor. The main principles used in this experiment were Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law. Kirchhoff's voltage law states that sum of all potential differences around a closed loop must equal zero. Kirchhoff's current law states that current entering a node must equal the current leaving the node. And finally, Ohm's law relates voltage, current, and resistance using the equation here. These principles allowed us to analyze the behavior of the circuits in this lab. In the DC circuits portion of the lab, a 47 ohm resistor and a 100 ohm resistor were connected in series with a battery. The current was measured at two locations in the circuit. At position I1, the current was 15.5 milliamps, and the current was also 15.5 milliamps. Reversing the ammeter leads did not change the magnitude of the current, but it did flip the sign of the reading. Next, the ammeter at I1 was replaced with a voltmeter. The voltmeter measured 2.89 volts, and the current through the second ammeter dropped to 0 milliamps because the voltmeter was placed in series with the circuit. Next, we measured the voltage across different components of the circuits. The voltage across the 47 ohm resistor was 0.76 volts, and the voltage across the 100 ohm resistor was negative 1.67 volts. It's negative for both of those. The voltage across the ammeter was approximately 0 volts, and the voltage across the battery was 2.89 volts. When these values were summed together, the result was approximately zero, which confirms Kirchhoff's voltage law. The voltmeter behavior. A voltmeter has a very high resistance. Because of this high resistance, very little current flows through the voltmeter. Instead, the current continues to flow through the rest of the circuit. This allows the voltmeter to measure the potential difference across the component without significantly affecting the current in the circuit. Using the measured voltages and Ohm's law, we calculated the resistance of each component. The 47 ohm resistor had a calculated resistance of approximately 49.03 ohms, and the 100 ohm resistor had calculated resistance of approximately 107.7 ohms. The wires in the circuit appeared to have a resistance of 29.7 ohms, which is higher than expected and likely due to measurement or contact resistance. The ammeter had an approximate resistance of 0 ohms, which is expected because an ideal ammeter should not significantly resist current flow. When a voltmeter is attached to the circuit, it technically alters the circuit. However, the ammeter reading does not change significantly because the voltmeter has a very high resistance. So almost all the current still flows through the resistors. Next, when the voltmeter is replaced with an ammeter placed in parallel with a 100 ohm resistor, the current through the other ammeter increases from 15.5 milliamps to approximately 61.5 milliamps. This occurs because the ammeter provides a very low resistance path, effectively bypassing the 100 ohm resistor and reducing the total circuit resistance. Next, we analyzed an RC circuit using a 1 farad capacitor and a 10 ohm bulb. The capacitor took approximately 8.5 seconds to charge and 11.9 seconds to discharge. These values were shorter than expected based on the theoretical model. Possible sources of error included incorrect resistance or capacitance, values or timing errors when measuring the charging and discharging intervals. The experiment was then repeated using a 20 ohm bulb. With the higher resistance bulb, the capacitor took approximately 57.67 seconds to charge and 39.27 seconds to discharge. This demonstrates that increasing the resistance in an RC circuit increases the time required for the capacitor to charge and discharge, which is consistent with the theoretical predictions. What if questions? Finally, we considered what would happen if a capacitor were charged without any resistor in the circuit. In the ideal model, the capacitor would charge instantaneously. This is because if the resistance is zero, Ohm's law predicts an infinitely large current, which would charge the capacitor immediately. However, in real circuits, this does not occur because all materials have some resistance, even including the wires, as we found. Therefore, the capacitor will charge very quickly, but not instantaneously. In conclusion, this experiment demonstrated how electrical circuits obey Kirchhoff's voltage law, current law, and Ohm's law. The DC circuit measurements confirm that the sum of voltages around a loop is approximately zero, and the current remains constant in a series circuit. The RC circuit experiment showed that increasing resistance increased the charging and discharging time of a capacitor. These results demonstrate how theoretical circuit laws can be applied to predict real experimental behavior. Thank you for your time.